So, Assalamualaikum warahmatullahi wabarakatuh. Today, we are going to present our fuzzy logic project, which is fuzzy logic control in smart fan. Our group consists of 7 members, which is Ani Hazri, Ahmad Khazuri, Khaira Amri, Muhammad Idlan, Muhammad Amar, Adi Azri, and also Amirul Nizam. So we are going to proceed to introduction. A smart fan is a device designed to improve indoor air quality by removing various pollutant, contaminants, and allergens from the air. It typically consists of a fan and filtration system that captures and filter out particles such as dust, pollen, pet dander, mold spores, bacteria, viruses, smoke, and other airborne particles. There are two scopes that we consider in this project, which is air quality assessment and also decision making. So for the air quality assessment, fuzzy logic allows SmartFan to assess and interpret air quality based on the data that been obtained from sensors by using linguistic variables and fuzzy membership. The system can analyze multiple factors such as dust, volatile, organic compound, and humidity of surrounding environments. For the decision making, fuzzy logic allows SmartFan to make informed decisions regarding the selection of modes of setting that be used. By considering all of the variables and fuzzy rule, the system can decide which modes suits well with the surrounding environment. So the significance of this project is intelligent control, air quality monitoring, handling uncertainty, and also fault detection. Intelligent control allow the smart fans to make decisions based on the current air quality condition. It helps to ensure optimal performance, reuse, and minimizing energy consumption. Air quality monitoring helps smart fan to continuously monitor and assess the air quality in the real time. After obtaining the result, the appropriate purification level that be required to maintain clean and healthy air can be determined. Handling uncertainty. It is useful in dealing with uncertain or variable condition. Equality can change throughout the day, but fuzzy logic can handle the inherent ambiguity of this situation. Fuzzy can make great decision although the input data is imprecise. For the fault detection, it can be used for fault detection and diagnostic in SmartFan. By measuring fuzzy variables and algorithm, we can identify abnormalities or malfunctions from a normal operation system. So there are one research paper that we refer in order to make this project, which is we retrieve from the ResearchGate fuzzy logic based fan controller of indoor air purifier fan. So we can see that there are several things that they consider in their research paper. So first, the research paper are trying to measure how the air purifier can help to keep the air clean. They're also trying to find what is the main features that be used to control the fan speed of the air purifier. So we apply this fundamental into our smart fan and we take temperature, dust matter, VOC meter, and room size as input and fan speed as output.
Next, I'll continue the presentation by explaining all of our inputs and output through linguistic variables, values, and membership function, and their graph representations. The first input of our smart fan fuzzy system is temperature. The temperature input tells us the temperature of the room the smart fan is placed in. So the temperature input is split into three linguistic values, that is low, normal, and high, and besides them are their respective membership functions. The second input would be the dust matter input. The dust matter input tells us the level of dust matter in the surrounding air, and similar to the previous input, that is temperature, the dust matter input is split into three linguistic values, that is low, normal, and high, and besides them is their respective membership functions. The next input is the VOC meter. VOC stands for volatile organic compound. This input tells us the level of harmful volatile organic compound in surrounding air, and uh, this input is split into four linguistic values, that is low, moderate, high, and very high. And besides them is also the respective membership functions. The last input of our smartphone fuzzy system is room size. The room size input concerns the size of the room the air purifier is placed in. And the room size input is split into three linguistic values, that is small, medium, and large. And besides the graph is their respective membership functions. Moving on to the output of our smartphone fuzzy system. So our output of fuzzy system is concerning the fan speed. The output will readjust the fan speed according to the input supplied to the system. So the output fan speed is split into three linguistic values, that is low, medium, and high. And the range of values for the output fan speed is between 0 and 2000.
So next we are going to explain about fuzzy rules for this project.
Or our fuzzy logic control system, we uses four variables that act as an input. The first one is temperature with, with unit of degree Celsius with the notation of L for low, N for normal, and H for high. Second one is dust matter, which is measured by milligram over cubic meter with the notation L for low, N for normal, and H for high. Third one is bulk matter with notation L for low, MO for moderate, and VH for very high. Variable number 4 is room size measured in square feet with notation S for small, M for medium, and L for large.
This table shows the summarization of input for the rule. These are the rules that we use in our project. For example, if temperature is low and dust matter is low and VOC matter is low and room size is small, then fan speed is low. The next example we can take as in rule 13. If temperature is low and dust matter is normal and VOC matter is moderate and room size is small, then fan speed is medium. So all these rules use logic N as the combination of temperature, dust matter, VOC matter, and room size to get an output.
Okay, so for the inference system, we decided to use the Mamdani style technique in our project, which include fuzzification, rule evaluation, aggregation of the rule outputs, and also the fuzzification.
So next is the sample input. So there are four fuzzy variables that we use for this project, which is temperature, dust matter, VOC matter, and also room size. So to do the fuzzy inference, we did three cases, which the first case is the temperature is 35, dust matter is 0.15, VOC matter is 50, and room size is 200. For the second case, temperature is 25, dust matter is 0.05, VOC matter is 80, and room size is 150. And for last case is temperature 10, dust matter 0.1, VOC matter 100, and room size 300.
Okay, so now for the classification, the first step we did is the classification, where we transform crisp values into fuzzy values, which we have evaluate these values and see where it belongs in the appropriate variables. So this is the for case one. We have input for input, which is temperature 35, and input 2 does matter, we choose 0.15, and input 3 VOC matter 50, and also for room size we choose 200. Then as we can see here, to find the value of degree of membership, we use the equation of straight line, which is y equals to mx plus c. And for example, for the first input, the value of temperature is 35, and then we just use the equation of straight line, and then we get the degree of membership, which is 1. And also, it's the same goes on to the input 2, input 3, and also input 4. Okay, so for case 2, it is the same as case 1, but with the different input values, which is for this one, input 1 for temperature, we choose 25, and for input 2, 0.05, and input 3, 80, and input 4, 150. Then we do the same thing, which is we find the degree of membership for each input, and then and also we write the fuzzy variables, which is for temperature is normal, and for input doesn't matter, we get a fuzzy variables which is low, and then for matter fuzzy variable is moderate, and also for input 4 room size, the fuzzy variable is medium. And then we use the same technique, which is y equal to mx plus c, to find the degree of membership for each input. Okay, so for the case 3, the first input, for simple input, we use temperature of 10 degrees Celsius, and the second input, which is decimeter 0.1, the third input is velocimeter for 100, and room size is 300. And then we did the same thing, which is by using the equation of y equals to mx plus c to find the degree of membership for each input, and also write down the correct fuzzy variables. Okay, now let's moving on to the rule evaluation. So this is a process that involves in converting classified inputs into a singular number that reflects the evaluation of the antecedents. When dealing with multiple antecedents, a fuzzy operator like AND or OR is employed. These results are then utilized in relation to the membership functions of the consequences. However, in this sample, we did not use OR since the rule that we use does not contain OR in its fuzzy rule. Then for case 1, there is a four rule that we use, which is rule 44, rule 45, 51, and also 54. And for example, for rule evaluation, for rule 44, if temperature is high, which is 1.0, 1.0 is the value of degree of emission that we have calculated in the classification, and dust matter is normal 0.3, and VOC matter is low, and room size is medium, then fan speed is high, which is 0.3. So why we choose 0.3? Because this called the n, where we choose the minimum values of the membership, which is 0.3. And also same goes on to the next rule, which is rule 44, 51, and also 54. Now for the second separate input, the rule that have been used is rule 47, where if the temperature is normal and decimeter is low and velocimeter is moderate and room size is medium, then fan speed is medium, which is 0 0.8. Okay, so for the last separate input, which is separate input 3, the rule that is involved is only two, which is rule 85 and rule 94. Where the value of output, which is 0.5 and also 0.3.
Okay, let's move on to aggregation. Okay, for the output for case 1, it is the combination of rule 42, rule 45, rule 51, and rule 54. And case number 2, the output is only from rule 47. And for case 3, the output is combination of rule 85 and 94. Okay, after we determine a aggregated fuzzy set, we move on to defuzzification. We are using centroid defuzzification method to calculate the center of gravity of this aggregated fuzzy set. From the case 1, the conclusion is when temperature is 35 degrees Celsius and dust matter is 0.15 and VOC matter is 50 and room size is 200 square feet, then the fan speed is 1700 RPM. Next, we repeat the same method for case number 2, and the conclusion that we get from the formula is when temperature is 25 degrees Celsius and dust matter is 0.05, VOC is 80, and room size is 150, then the fan speed is 900 RPM. Okay, lastly, for case number 3, using the same method,
After the calculation, we can conclude that when temperature is 10 degrees Celsius, dust matter is zero point 0.1, VOC is 100, and room size is 300. Then the fan speed is 1240 RPM.
So in conclusion, fuzzy logic proved that it was a great technique for smart fan. By using fuzzy logic algorithm to design and operate the smart fan, several advantages can be achieved. Smart fan can handle multiple sensors to monitor various air quality conditions and can consider multiple factors simultaneously and prioritize it based on the importance of the factor. As a conclusion, the application of fuzzy logic in smart fan can enhance their performance, and it also can boost the efficiency of smart fan in order to improve the air quality. That's all from us. Thank you.